We are going to start this semester by learning all about vectors. And you may have learned about vectors before in trigonometry class or in physics if you've already taken Physics 1. In order to define a vector, first we're going to talk about a scalar quantity. And scalar quantities are most likely what you've been using in all of your math classes up until this point. A scalar quantity is a quantity that has magnitude but no direction, and the magnitude we represent by a number. So anything that you can measure or calculate that will have a number answer will be a magnitude or a scalar. A couple of examples of this are temperature. When we measure temperature, it doesn't make any sense to assign a direction to it. Also area, and along the same lines as area, volume. All of these quantities have a magnitude, but it makes no sense to attach a direction to them. So what's different about vectors is that a vector quantity has both magnitude and direction. And if you've already taken physics, you may know that force is a vector. When you apply a force to something, you are applying both a magnitude, usually in terms of pounds or newtons of force, but you're also applying that force in a particular direction. Another example is velocity. You may, in other classes, have used the word velocity when really you were just talking about speed. Speed is the magnitude portion of the velocity vector, but to be 100% accurate, technically velocity has both magnitude and direction. Another example that we will probably work out some applications for, displacement. And displacement is how you describe the movement of an object from one position to another. So I don't want to say that I moved the desk 5 feet, because that does not give me an accurate representation of what the new position is, because there is an entire circle of radius 5 feet of points that could be used when we only say a magnitude. So for displacement, we also have to say a direction. So like I moved the desk 5 feet to the right, or I moved the desk 5 feet west. So displacement is also a vector quantity. Most of these problems, when we deal with vectors, we're going to want to make some sort of diagram. So a vector can be represented by a directed line segment. It's a line segment in that it's got a fixed starting point and ending point, and it's a directed line segment because there is a particular direction to this vector. There is a specific direction of motion. We are going from vector P from point P to point Q. Well, the nice thing about vectors is that we can take that vector and we can slide it all around the plane and put it into any position that we need to. And the important thing with vectors is that we have to preserve the magnitude. The magnitude of a vector is represented by its length, and then the direction, which we'll talk about later, is represented by a standard position angle. As long as those two are preserved, then we can slide this around anywhere we want to, and it would still be considered the same exact vector. So two vectors are equivalent if they have the exact same magnitude and direction. And if we take the set of all directed line segments that are equivalent to a particular directed line segment, such as PQ here, that's going to give us a vector in the plane. So a vector is not tied to specific starting and ending points. We call P the initial point, and we call Q the terminal point. The terminal point is where our arrow is pointing. So to represent the fact that we really could slide this anywhere we want to and not anchor it down at P and Q, we try to move away from this notation of PQ with an arrow on top, because that ties us to those 2 points, and instead just write our vector as a lowercase letter with an arrow on top. If you're going to use the initial and terminal point notation, then we always want the initial point first and the terminal point second. But you'll see in just a few minutes we're going to be sliding our vectors around all over the place. So we don't want to use those 2 points we started with. We just want to call it vector v instead. So we know that we can write a vector in terms of its initial and terminal point. We could also use a single letter with an arrow on top, like I did up here with my v. You may also see in the textbook or MyLabs Plus that they sometimes write just a boldface letter for a vector and they don't put the arrow on top. In my notes, I'll never have boldface letters. I can't efficiently distinguish in my handwriting regular letters to boldface letters, so I always use the arrow when I'm writing a vector. So since we have the freedom to slide this vector around anywhere we want a good concrete mathematical way to describe a vector, and right now I'm having to describe it with 2 different points. But since the position doesn't really matter, what we're going to focus on more is vectors that are in standard position. When the initial point of a vector is at the origin, 0, 0, we consider it to be in standard position. And if we're doing a problem that works with a bunch of different vectors, and we slide all of them into standard position, then they will all have an initial point of 0, 0. So the only thing that will be different about all of our vectors are their terminal points. So that new terminal point, once we slide it into standard position, is really important, and it's going to be how we represent a vector in standard position. So I'll show you a quick little example with a graph. Let's say we've got initial point at -4, 0. That's our P. And then we've got a terminal point at -2, 3. That's our Q. So if I want to take this vector that right now is anchored down at 2 specific points, and I want to slide it into standard position, what I'm wanting to do here is take point P and move it to the origin. And I'm allowed to do that as long as I preserve my magnitude and my direction. So the way that we preserve magnitude and direction is whatever movement you have to apply to P to get it to the origin, you do the exact same movement to Q. So to get P to the origin, I'm going to have to move it 4 places to the right. So to preserve magnitude and direction, I'm also going to have to move Q 4 places to the right. So it goes from -2, 3 to +2, 3. And if we now draw that new vector, it should look identical to the one we just had. We've just changed its position. It's still the exact same length. It's still pointing in the exact same direction. So technically, it's still the same vector. So there's a nice easy formula that we can use to get standard position. If we have initial point P at x1, y1, and terminal point Q at x2, y2, we said anything we've got to do to P to get it to 0, 0, we'd have to do the exact same thing to Q. So this new vector can be written in component form, and when we're using our terminal point to represent a standard position vector, we always use these diamond brackets. To move x1 to 0, I'll have to subtract x1, and I've got to do the exact same thing to my Q. So my new terminal point will be x2 minus x1. And then to move y1 to 0, I need to subtract y1 from it, And then we need to do the same thing to our Q point. So the new y coordinate would be y2 minus y1. This is called component form for a vector, and it tells us a lot of different things about the vector, but for right now it tells us two important things. It tells us that if you see the diamond brackets mean vector in standard position. And standard position means initial point 0, 0, and then terminal point is our component form. So we have terminal point x2 minus x1, y2 minus y1. The other important thing it tells us is change, how the x value is changing and how the y value is changing. Anytime we use subtraction in math, it represents a change. So this is going to be very helpful to us when we start talking about magnitude and direction. If I've got a standard position vector, and its components are v1 and v2, that means to get from the start of the vector to the end of the vector, we have to go right v1 units and then up v2 units. And because that vector is not dependent upon its starting and ending positions, these two numbers are really describing the change from the starting point to the ending point. So we can move this vector anywhere we want, and as long as we apply this specific v1, v2 change, we will be able to figure out the terminal point. So the way that we put a vector in standard position is we subtract those terminal components. We take the terminal components and subtract the initial components. So let's try a couple of examples. And the first one, we're going to draw it out to see exactly how it moves. So we want to find component form for vector PQ. And I'm going to give you the P and the Q. So if P is the point 2, -1, and Q is the point 0, 3, so 2, -1 is right here. There's our P. 0, 3 is here. There's our Q. And there's vector PQ. I know I'm starting at P and ending at Q because of the way it's written. We always have initial point first, terminal point second. But now we want to slide this into standard position, which means I want to move P to the origin. If we follow our formula, the formula says terminal component minus initial component. Terminal component minus initial component. We see that we get component form of -2, 4. That also happens to be the new terminal point of our standard position vector. If I want to preserve magnitude and direction, I had to move P left 2 and up 1. So I have to do the same thing to Q. I have to go left 2 and I have to go up 1. And that will give me my new Q point. And our vectors look exactly the same. They've got the exact same length, which is our magnitude, and they are still pointing in the exact same direction. So it's still the exact same vector. The only difference now is the red one is in standard position. So let's try another one really quickly. I'm not going to draw this one though. Let's say P is -2, 5, and Q is 1, 1. So if you kind of imagine where these are located, point P is in quadrant 2, and point Q is in quadrant 1, but it's got a much lower y value. So if we were to draw this, the vector would kind of be pointing down to the right. If we apply our formula, we're going to do x2 minus x1, so 1 minus -2, and then y2 minus y1, which is 1 minus 5. So the component form for this vector is 3, -4. And this is the terminal point if we slide our vector into standard position. So we said from the original P and Q, it seemed like it was pointing down to the right. We can confirm that now by looking at our component form, because if our initial point's now 0, 0, the terminal point is 3, -4, which is pointing down to quadrant 4, which is down and to the right. And we could draw a picture for this one the same we did with the last one.